Bismillahirrahmanirrahim. In this lecture, I will talk about liquid drop water, and it is composed of many important terms, including the volume term, surface term, Coulomb energy term, asymmetry term, and the pairing term. So I will describe in detail about all these terms and then the very important objectives of the liquid drop model. So these will be the learning objectives of the liquid drop model. The first is you can calculate the binding energy by using the semi-empirical binding energy formula. And this is the semi-empirical binding energy formula we are going to discuss in detail in this lecture. And other important objective of this lecture is to calculate the mass of an atomic nucleus by using the binding energy formula. So this is the simple equation we will be using to calculate the mass of the atomic nucleus, because here is the binding energy. So we will be using the binding energy to calculate the mass of the nucleus. So these are very important learning objective of today's lecture on the liquid drop model. So the first, let's have a brief about what is the liquid drop model. So it treats the nucleus as a drop of incompressible nuclear fluid, as the the fluid of the water or the drop of the water as well. So there are many analogies between the behavior of a nucleus, so that the liquid drop, and hence it was assumed to be like a liquid drop. So there are several similarities, and the three I have mentioned over here. The first one is the nucleus tends to be spherical in shape, as the pattern demonstrated by a liquid drop. So the second similarity is the nucleons, which are the sum of the neutrons and the proton, congregate to shape a nucleus as molecules assembles to shape a liquid drop. So the third one is the similar to the liquid drops, the nuclear density is uniform in its largest space and lessens at the surroundings or the periphery of the nucleus of the drop. So these are the similarities on which we are calling it a liquid drop model, because it is resembles the nucleus is resemble as the drop of a liquid. That's why this is called the liquid drop model. So this is just to refresh your knowledge, because we are actually in calculation, we are explaining the semi-empirical formula, but the way of the calculation is the same as you have already learned in the previous lectures. And you can go to my other YouTube lecture, and in which I have explained all these factors to calculate the mass defect and the binding energy and the average binding energy. So just to refresh your knowledge, so in the similar way, we will be using the liquid drop model of the semi-empirical formula to calculate the binding energy and the mass of the nucleus. So like in a simple way, you can calculate the mass defect, and it is the mass, the calculated mass. Calculated mass means the based on the number of protons and the neutron. This is the mass of the neutron, n is the number of neutron, mass of proton, mp is the mass of proton, and z is the number of protons, and minus this is the mass of the nucleus. This is actually the experimental mass. So it is a general statement about this one. The mass of the nucleus is always less of the mass of its constituent element, that means the sum of the protons and the neutrons. So that's why this value must always be in positive form. So the energy release in the form of the binding energy which bound the nucleons within the nucleus. This is the basic reason why the nucleus are stable nucleons are stable within the nucleus. So other, if you want to calculate the, again, what I have done over here, binding energy. So actually you have to convert the mass into energy, and you can use the simple Einstein equation, E square mc squared. So I am multiplying the c square to the whole equation, or you can simply, if you want to convert the energy into mega electron volt, then you just multiply this factor 931.5 instead of the c squared by using this simple conversion unit. It will directly convert into the binding energy and energy in mega electron volt. So if you further want to calculate the average binding energy, and just you have to divide with the nucleons, that means it is the mass number, and this will directly convert the binding energy into the average binding energy. So from the average binding energy, this is the graph. In this video I have explained in detail. So actually the average binding energy of iron 56 is the highest among the other nuclide. So before uh, iron 56, these are the lighter nuclides, so they tend to fuse together to form the to move towards the iron 56 after releasing the energy. And in the similar way, these are the heavier nuclides, so they if they want to move towards the iron 56, so of course the fission process will occur, and then they will split into the lighter nuclides and moving towards the iron 56. And this actually fusion, or the fission, that is the, it is also the direction of the release of energy. So if you want to calculate the mass of the nucleus, and simply this is the same equation, that means our purpose is to calculate the mass of the nucleus over this. So you can move this to the left hand side and binding energy to the right hand side. So this is just the rearrangement of the binding energy formula. And again, uh, uh, dividing c square by the whole equation, this will become E B over c square, and there is no need to use the detailed calculation again by using this conversion unit. You just divide 931.5, so this energy is converted into the atomic mass unit. So this is the mass of the neutrons, proton minus this one, and will give you the mass of the nucleus. So actually this is the simple way of the calculation, and liquid drop model or the semi-empirical formula is the more advanced form of this calculation to accurately or calculate the binding energy as well as the mass of the nucleus. So moving to the equation. So as I have already said before, there are the different terms, and the first term is the surface term. So surface term is this is the constant for the first term is the volume term, and this is the AV is the constant for the volume term, and A is the mass number of the nuclides. So in the whole equation, we are just using the number of protons, neutrons, or the in other way it is the mass number. So there is nothing. The whole equation seems to be very long, but it is very simple because there is no other than the number of protons and neutrons, or the mass number are present. So let's have a look on the why we are having the volume term in the semi-empirical formula. So volume is like, you have just a look at the nucleus. Nucleus is like, as we have discussed before, it is the drop, look like a drop of the liquid. So what is happening here, if you just, the red balls are the number of protons and the white are the neutrons. So the volume is how it is going to be, one protons or the one neutrons is going to interact with the neighboring number of protons or the neutrons. So let's have a look on this neutron. So this neutron is attracted towards the two protons and neutrons, again protons and again neutrons. So these five are the maximum interaction of this neutron with the neighboring protons and the neutrons. So this will happen like if I look at this proton, and this is going to be interacted with the six neighboring neutrons. So that means uh, this protons or this neutron has a fixed number of interaction within the nucleus. So it is independent of the mass number. So why it is the independent of the mass number? Because if you just increase the volume, so these interactions are not going to change. This will remain the constant. So, however, but the volume is increasing. There are more number of protons and neutrons within the nucleus, and so the volume is going to increase. And when the volume is going to increase, it is having the direct relation with the binding energy, and of course, it is having the positive contribution to the binding energy. So, more will be the volume, more will be the volume mean, more will be the mass number of the nuclide, more will be the binding energy. And in the previous video, you can check, you have also calculated the binding energy. So binding energy having the direct relationship with the mass number. So it is increasing from hydrogen to the, let's suppose the uranium 92. So this is all about the volume term. So this is proportional to the binding energy, and the simple way, if you want to calculate simple the volume term, so you just multiply the mass number with the constant of the AV. This is the volume term constant, and these are given and these are depends on the different models. So we will discuss later in this lecture what are the values of these constants. So second term is the surface term. So surface term is equal to AS, A power 2 by 3, and this is called the surface term. And this term also describe a spherical liquid drop of incompressible fluid with a contribution from the surface and scaling the value of A 2 by 3. So both the terms actually, the volume term and the surface term contribute to the spherical shape of the nucleus or the liquid drop of incompressible liquids. So why we call it the incompressible liquid? Because there is the certain limit of the interaction, and when you further compress to each other, they are going to repel to each other. So that means further they are incompressible. So that's why it is called the incompressible fluid. So, so the surface, this is the surface of this nucleus or the liquid drop, and you have a look what is the difference between the volume term and the surface term. Surface term is only responsible towards the number of protons and the neutrons present at the surface. So the particle at the surface of the nucleus are not completely surrounded by the other particles. So, and this is as a similar effect we discuss in the liquids, and it is called the surface tension effect. So this effect is very similar to the surface tension effect. That means the molecules at the surface are not equally surrounded by the other molecules. So let's suppose this proton having the interaction with this proton, neutron, and this side. So the interaction are there, but there is no interaction on the upper side. So this is simply the surface tension effect. So the number of nucleons positioned on the surface of the nucleus have lesser role in stabilizing the nucleus. Therefore, surface area has a negative contribution in the equation, because they have the more will be the tension on the surface. That means these are going to actually to destabilize the nucleus. So that's why it is having the minus sign. So why it is equal to this formula, as we have discussed in the previous slide. The volume is proportional to A, and the geometric radius, of course, it should be proportional to A 1 by 3, and the surface area will be proportional to A 2 by 3. That means just I am going to multiply the surface area is the A square, square multiplied by 1 over 3. That will be 2 over 3. So surface term will be equal to 2 over 3, and you have to subtract to calculate the binding energy from the volume term. Third term is called the Coulomb terms, and again this is the nucleus, and there are number of protons and the neutrons are there. So Coulomb term describes the actually the repulsion between the uniformly distributed protons, and it is proportional to the number of protons pair g square over r, and this r is the radius and is proportional to a 1 over 3, as we have discussed in the surface term. So actually what is happening here, this is the due to the repulsion between the protons and the protons, and there will be no repulsion between the neutrons, because neutrons are not having any charge. So there will be only the repulsion between the proton, and because of the repulsion between the protons, it effects and it lowers the binding energy. So that's why the sign of the Coulomb term is in minus, and this is the simple formula to calculate the Coulomb term. And this is the z are the number of protons, again number of proton minus 1 divided by A is the mass number, power 1 over 3, and this will be the Coulomb constant, term constant, and having the fixed value, and this we will discuss in later on. So moving to the fourth term, and this is called the asymmetric term. So if you asymmetric term, like here asymmetric, first what is the symmetric? Symmetric mean when number of protons are equal to the number of neutrons, as in case of the oxygen. Atomic number is it is the oxygen 16, calcium 40, 8 16, 20 40. So the both protons and the neutrons are same in both of the cases. So this effect is called the symmetric effect. And here you can also have a look at the symmetric. What is symmetric? That means the same number of protons, proton, neutron, proton, neutron, proton, neutrons, and these are the symmetric in nature. So, and these four neutrons are left. That means this nucleus has the asymmetric effect. So asymmetric effect means when neutrons are not equal to the protons, and then the nucleus having the asymmetric term. And this is because if you have a look on all the nuclide or the elements of the periodic table, so you can say the heavier nuclide contains more number of neutrons than the protons, because extra neutrons are necessary for the stability of the heavier nuclide, and they actually provide some sort of the attraction between the neutrons and the proton, or it is more reasonably to say that to compensate the repulsion forces between the protons. So this is I was discussing about this one. So all these are the asymmetric terms, and this is another example to differentiate between the symmetric and the asymmetric. Let's suppose mass number 16. So there are and maybe the same number of protons and the neutrons. If the number of protons and neutrons are same, 8 number of protons and 8 number of neutrons, then n minus z will be equal to 0. That means this set is symmetric in nature. So if we are having like this type of the contribution, then number of protons are 6, number of neutrons are 10. So up to here, this is the symmetric and these four are the unsymmetric. And you can directly calculate by using this formula. That means 10 minus 6 will be equal to 4. So due to this unsymmetric effect, it is having the high energy. So that's why due to this high energy, it is going to actually destabilize the nucleus, because with the symmetric effect, or with the same number of the protons and the neutrons, they are having the stable nuclides. So due to this instability, actually, this is also having a minus contribution in the semi-empirical formula. So this is the reason of using this minus, and this is the formula to calculate the asymmetric term, and this is the mass number minus 2z square divided by the mass number. Z is the number of the protons. Or simply you can use this n by z, because a equal to n plus z, and when you put the value of n plus z, so z plus z minus 2z will be equal to minus c. So it will be equal to n minus c. Either you can use this n minus z, or you can use a minus 2z whole square. So this is the, because different books are using these two different forms to represent the asymmetric term. So you can use any one of them. These are having the same values. So this is all about the asymmetric term. And now the last and the fifth term is the pairing term. So how the neutrons and the protons are paired within the nucleus, and this is called the pairing term, and this is shown by the sigma, and it is having the value of a p. Again, this is the constant. This is the power is also constant. It depends on the model which we are going to use. And A is the mass number of the nuclide. Let's suppose if it is having the power of minus 1 by 2, and this will be the A minus 1 by 2, maybe minus 3 by 4. So power will be minus 3 by 4. These are having the constant value. We will discuss in the next slide. So the pairing term, actually, this is the effect of this coupling, and neutron or proton bonding is more effective than the neutron proton or proton neutron bonding. So here these are the bonding are shown. This between the neutrons, and these are left. So that means these two are not paired. One proton is not paired, and one neutron is also not paired. So because it now in the previous terms, this we have discussed over here. The volume term is in positive, and surface term having minus. Coulomb term is also minus, and asymmetric term is also minus. And the reason I have already given in the previous slide. And here it may be positive and it may be minus. So here just a minus is given, just as shown in the formula, but the value may be in the minus or in the plus. And this I'm going to describe when the value will be the minus, when will be the 0, and when will be the plus. So let's suppose the first contribution, when the A is even, A is the mass number. When A is the even, then there will be the and Z number of protons are also even, and then of course number of neutrons will also be even. So even you can just remember this one, when the number of protons and neutrons are even, then this pairing term having the positive contribution towards the binding energy. Why it is having the positive contribution? The reason is written over here. because the even number of protons and even number of neutrons, uh, due to this principle, very stable and having the paired spin. So the when the pair is spin, because both neutrons and the protons are in even, so all spins will be paired. So that means it is having the most stable one and contribute to the positive contribution to the binding energy. Other one is the when A is even, or you can say when A is even and Z number of protons are odd, then number of neutrons will also be odd. So it is easy to remember when the both number of protons and neutrons are odd, then it, it is going to contribute minus to the overall semi-empirical formula or the binding energy formula. And why it is the minus? Because nuclei with the odd number of protons and neutrons are mostly unstable. So because they are unstable, so these are having the minus contribution to the binding energy formula or semi-empirical equation. So the third or the fourth case is when A is odd, or you can say when Z and N are odd or even. So if maybe there may be a two possibility when the number of protons are odd and number of neutron are even, or number of protons are even and number of neutrons are odd. So even will be the paired and the odd will be the unpaired. So that means one protons or the neutrons will be the paired within the nucleus, and the others one will be the unpaired. So it is going to contribute zero to the overall binding energy formula. So this is the all about the pairing term. So now we are moving towards the calculation, how we can use this semi-empirical formula to calculate the binding energy, and then we will use this binding energy in this formula, and these are the masses of protons and neutrons. You can calculate the mass of the nucleus or the atomic nucleus. So first are the how you can calculate the coefficient or the constant for all different terms we have explained in the previous slides. So actually these coefficients are calculated by fitting to experimentally measure masses of nuclei. That means these value can vary depending on how they are fitted to the data. So that's why these are the four models have been shown over here. So there may be the other models which can fit the experimental data, and uh, these value you can use to calculate the binding energy. So let's suppose if you want to apply this least squares fit method 1, then this is the volume term. The constant for the volume term will 15.8, constant for this phase term 18.3, Coulomb term 0.714, and asymmetric term 23.2, and these AP or KP are for the pairing term. So AP is what is the coefficient of the pairing term, and Kp is the power of the pairing term. So let's suppose if the value of 12 and this is minus, so it will be the 12 A over 1 by half. That means just I am moving this to the denominator side, so it becomes positive, and if you move to the numerator side, it becomes a minus. So just there is no difference. So as we have earlier explained for the parent term, when it is even contribution, even number of protons, even number of neutrons, then it is having the positive contribution. So positive contribution is coming from this even combination, and these are the constant over here. So you can just put the value and value of A and get the value of the pairing term. So if there is order combination, then of course just the sign will change and the rest will remain the same. And in other case, even odd or odd even combination, there is zero contribution of the pairing term towards the binding energy formula. So here you can use if, so what is left only this mass number, number of the protons, mass number, number of protons. So just you have to put the number of protons or the mass number in this energy formula. By using this constant, you will get the binding energy. So this will be the more accurate as we have calculated before by using the mass defect formulas. So again, if you want to apply this method, so the constants figure are going to change. The rest will remain the same, and the rest there is only the mass number and the number of the protons or the atomic number. So by using this, so again there is the other constant are there to calculate the binding energy of the nucleus or nuclei. So like in this case, it is the value of AP is 34. That's why this is the 34 and the power is minus 3 by 4. So power will mean the minus 3 by 4. It is multiplied by, this will be minus 3 by 4. So if you move here to the down term, that means to the denominator side. So it will become positive. Similarly for these other terms as well. So let's have a look on one of the calculations. So there are the three different calculations to calculate the binding energy by using the semi-empirical formula. In case of the calcium, atomic number 20, mass number 40. So I am using the least square fit method too, like here I have explained over here. So by using this method, I'm going to calculate the energies, binding energies of these three nuclide. So these constant are coming from the previous slide. So I will just put the mass number is 40, mass number 42 by 3, atomic number is 20, 40, number of neutrons and the protons, again 40 minus 20, 20, and this is going to be the, to calculate the symmetric term, and then it is the pairing term. So because there will be the same number of proton neutrons, so this will become 0. So let's vote for this one. So what I have done over here, so you just multiply 15.76. This is the mass number is the 40. 40 multiplied by this will be the value 630. Then the surface term, again it is the 40 power 2 by 3 multiplied by this factor. This will be the minus 208, and minus is due to the formula which is given over here. So if you face difficulty to calculate this 2 by 3, so just divide 2 by 3, and what is the overall number? You just take the power of the A, 40 power the 2 by 3. You may calculate first square and then 1 by 3, or you can calculate first 2 by 3 and then just take the power of A by using this factor. You can easily calculate this one. So this is all about for the rest of the terms, and for the pairing term, it is 34 as for the this method, and the power is minus 3 by 4, and you just have to put the value of A is in this case 40, and similarly you can do for the silver and the uranium. So I am going to, so here is the, actually this is the calculated by using formula, and this is the major value. So you just have a look how close is this value with the calculated value. Let's have another calculation by using another model. So this is the example for the uranium 92 to 38. And again, number of protons 2, mass number this, number of neutrons this minus this will be 146. And for the volume term, the constant again, I'm using another model not presented before. So 15.56 multiplied by mass 238, giving the value of this. Again, this is the mass 238 power 2 by 3 multiplied this 666.71. Similarly, you can do for the Coulomb term and for this symmetric term and for the pairing term. And pairing term, this is the 12 power minus 1 by 2, and here it is the calculation of this one will be 0.78. So because there are even number of protons and even number of neutrons, that's why this is having the positive contribution towards the binding energy formula. So actually these are the sum of all the terms: volume term, surface term, Coulomb term, asymmetry, and the pairing term, and this will give you the value of 1805.10. And this model is more close to the major value, which is the 1802, as compared to the this model. So this is how you can calculate the binding energy, and this is more accurate as compared to the binding energy calculated by using the mass defect. So this is the last slide to calculate the nuclear mass or the atomic mass by using the semi-empirical formula. This I have discussed in the second slide. So similarly, these are the number of protons, mass of the proton, number of neutron, mass of the neutron. This is the binding energy multiply c square. So there is no need to divide with the c square and then to convert into the energy mega electron volts. So simply I will be using this conversion unit. So let's see what is happening. 92 protons and one mass of proton is this. 146 neutrons and mass of one neutron is this, and minus this is the energy we have calculated in the previous example, like here in this case 1806. So I'm going to divide with 931.5, and this will give you the value of this. So just multiply and plus minus the final value will be 238.071126 atomic mass unit, or you can simply say U, or the unified atomic mass. So here there are two ways to calculate. One, this is a proton. If I put the value of the mass of the proton, that means mass of the hydrogen instead of the mass of the proton. So the difference is only the mass of proton. So I'm putting the mass of proton like in case of the hydrogen, because it is also a proton. So then this will remain the same, and this will be the value of this calculation will be 238.121634 unified atomic mass unit. So experimental value is 238.124. So how you can now see what is the application of this nuclear drop model. You can exactly and very closely calculate the experimental very closely calculated the mass of the nucleus or the atomic mass very closely to the experimental mass. So this is the application of the nuclear drop model. That means you can calculate the binding energy more accurately as compared to the calculated by using the mass defect, and you can calculate uh, the nuclear or the atomic mass by using this semi-empirical formula. So these two were our objective, which I have mentioned at the start of the lecture, and I explained throughout the different slides, and concluding on the objective as the application of the nuclear drop model. So thank you for watching and tune to the next lecture.